we know that x cubed minus 1. We don't always remember this one, but this is factorable as well. It starts off with an x minus 1, but what's left over is x squared plus x plus 1. This is not a lot to go on, but we might start thinking that this x minus 1 is a factor of anything that looks like x to the n minus 1. And we might start wondering what's left over. There are a couple of ways that we can get at this. One way would just be to use division. So notice that if x squared minus 1 is x minus 1 times x plus 1, then that means in the division realm, we could say x squared minus 1 over x minus 1 is x plus 1. In terms of division, we could say x cubed minus 1 over x minus 1 is x squared plus x plus 1. Nothing really fancy going on here. If 6 is 2 times 3, then 6 divided by 2 is equal to 3, and 6 divided by 3 is equal to 2. This is just 3 ways of saying this, communicating the same relationship between 2, 3, and 6. This is how multiplication and division are related. It's no different if I trade my numbers into polynomials. So you might want to speculate as to what's going on if I have x to the 4th minus 1. If we believe that there's a factor of x minus 1, we try to figure out what's left over. We could get there by doing division. And if you thought I was going to pass up an opportunity to do a long division of polynomial problem in trig class, then you just haven't been paying attention to what I do in class. This is going to highlight this is going to tell us how to write these, what's always going to happen. This is what we're going. When we write polynomials, we don't have zeros for placeholders. I got to throw in some placeholders. Because I've got a number like 1001, I got to put a couple of zeros in there for the 0 hundreds, the 0 tens. So we got to do the same thing here. How many times can we subtract x from x to the 4th? That's x to the 3rd times. X cubed times x is x to the 4th. X cubed times minus 1 is a minus x to the 3rd. And then we subtract. The x to the 4th cancel because it has to. That was by design. That's what we wanted. And then 0 minus a negative 1 is x to the 3rd. And then how many times can we subtract x from x to the 3rd? That's x squared times. And at this point, we should start to get suspicious. Isn't this just going to repeat with one less degree? And the answer is yeah. X squared times x is x to the 3rd. X squared times minus 1 is minus the 3rd. And we're going to subtract. X to the 3rd minus x to the 3rd cancels out. 0 minus a negative 1 is x squared. So we can see where this is going. X to the 4th minus 1 divided by x minus 1 is x cubed plus x squared plus x plus 1. We can also get there through factoring because we're at x to the fourth. So we might also look at this as x squared minus 1 times x squared plus 1. If I break the x squared minus 1 into x minus 1 times x plus 1. If I multiply x plus 1 times x squared plus 1, I get x cubed plus x squared plus x plus 1. So this makes us start to guess. X to the fifth minus 1 over x minus 1. We just start at 4 and go down, and the answer is yes. So x to the fifth minus 1 over x minus 1 is x to the fourth plus x to the third plus x squared plus x plus 1. Any questions? Everybody agree that this is what will happen? Of course, that's just proof by authority. I'm the authority, and I said this is what happens. And you're like, oh, okay. Proof by threats with more work. Are you sure that that's how it's going to work? I don't know. Maybe we should divide it and find out. And it's like, whoa, 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 no, 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 no. That's cool. It's cool, man. Let's not do any more division. Defense stipulates that this is how it's going to work. So in general, if I have, let's say, something massive, like an x to the, actually, we're going to go the other way. Let's suppose I have this huge polynomial that starts off with a 1 plus x squared plus x to the third plus, just keep following this pattern all the way up to x to the 17 and then x to the 18, and then I got tired of writing stuff. That's like 19 terms that I don't want to have to punch into my calculator. But fortunately, there's a plus sign. The 4, x to the fourth, x to the third, x squared, x and 1 has an x to the fifth minus 1 over x minus 1. So this is going to be an x to the 19 minus 1 over x minus 1. So rather than typing in 18 terms or 19 terms down here, I can just type these two and divide. That is pretty cool. Any questions? Is everybody okay? Now that raises a question. Why would I care about this particular polynomial? Who cares about this polynomial? My thesis is everybody over the age of 18 needs to care about this polynomial. Everybody over the age of 18 who thinks they might want to retire someday needs to care about this polynomial and this relationship in polynomial. So here's why. Let's suppose that we invest $100 into an account that will increase by 9% each year. Now you might look at this and say, dude, we were just talking about polynomials, and now you're talking about exponential functions. Those are completely separate chapters. I totally remember algebra. They're completely separate chapters. Why are you doing this? And it's true, this is an exponential function. If we increase by 9%, that means we're going to multiply by 1.09 each year. One, because you get to keep the money that you put in. The 0.09 is the extra 9% that we added to the 100% that we put in. That's 100%. So if something is increasing by a percentage, it's increasing by multiplication. If it was 12, then we multiply by 1.12, and so on. After 1 year, nothing surprising here. After 1 year, our $100 has become $109. Two more copies. It only took us a year to save for. After 2 years, we're going to take the 109 and multiply by 1.09. And I won't be able to multiply these without messing it up. So hopefully I bought a calculator machine. $118.81. But this is not how we want to read what's going on here. If I want to know what's going on after 10 years, I don't want to have to multiply all 10 products. I want to read this 109 as 100 times 1.09 once. This 109 came from 100 times 1.09. And then we multiplied by 1.09 again. So what we're looking at is 100 times 1.09 twice. Because that's what exponents mean. Exponents indicate repeated multiplication. We multiply by 1.09 times. So if we grab our calculating machines and multiply 100 times 1.09 to the second, 118.81. Not trying to hide things in the glare. So now we see an exponential function that says after 3 years, we just do the same calculation, but with 3. what we're seeing is some exponential growth. A lot of times people like to say something is growing exponentially when they really just mean things are growing fast. But it sounds fancy to say it's growing exponentially. And it just sounds so basic to say it's growing fast. Don't do that. Because if you say it's growing exponentially, I'll say, oh, wow, what percentage rate is it growing? And if you don't know, then you're just saying exponential when you want to say fast. Just say fast. It gets the point across just fine. When you say exponential, you mean something very specific. Growing by multiplication, geometrically. So what we want to notice here is that all we did was for this 1326.77 was 30 years ago, take $100 and put it aside. Put that $100 to sleep for 30 years, and it comes back and it's 1326.77. Hopefully, 9% is beating inflation over those last 30 years. We can use this in reverse. If we just want to know how much we need, let's suppose that we want to figure out how much we need to get to a certain target after 30 years. We can just divide it by this 1.09 to the 30. Notice that if I change my 100, because of the where the 100 sits, if we switch to, let's say, 500, we're just going to take our 1326 and multiply it by 5. 500 times 1.09 to the 30 is 6633.84. We divide that by 5. It's 5 times the 1326.77. So if we say we want $500,000 in 30 years, we can divide by this 1.09 to the 30th. And so we could say talk about the question in reverse. How much will we have to put aside now so that in 30 years, the answer is $500,000. The balance is $500,000. And all we have to do is divide, because that's how multiplication and division works. 500,000 divided by 1.09 to the 30th. I should be careful with my parentheses, but my calculator knows the order of operations. It will first take 1.09 to the 30th power and divide 500,000 by the result. So that means we would need to put aside $37,685.57. That's going to be money that we have to put away and ignore for 30 years. Yeah, that's pretty rough. This is not typically how we make preparation for the future. We don't take a giant stack of money that we don't have and not use it for 30 years. Some people do. But they have more money than they really know what to do with, so keep it. Let's come up with an alternate plan. Instead of just putting $37,000 aside once, let's start putting aside small amounts. Seems kind of a lot to ask for $37,000 right now. Let's start with something more reasonable. Let's say 20. But we're going to do this every month. We're still going to have the nominal 9% each year. We need a way to approximate what's going on with this 9% each year. So I'm just going to divide that by, see, we're doing this monthly, divide it by 12. We're just creating a model to get some ideas. It's not important that whether this is how it works or how it doesn't. We're just trying to get an idea. 9 divided by 12 is 0.75. So we'll be increasing by 0.75% per month, right? 9 divided by 12. 9 divided by 12 is 0.75. It's in percent. Increasing by 0.75 is multiplying by 1.0075, because I'll take the 0.75. That's as a percent. Percent means divided by 100. And then we'll add 1 because we get to keep what we start with, 1.0075. But we're going to multiply by 1.0075 each month. This works out to a little bit more than 9%. So we would have to adjust things, probably with some continuous scale, because if we take 1.0075 and do this 12 times, we're actually increasing by 9.38%. So it's a little bit higher. But we're just trying to get an idea about how things work. So here's what we're going to start doing. Immediately after our first deposit, the balance is just going to be $20. That 20 is going to be our first deposit. Immediately after the second deposit, the balance is going to be the new $20 that we just put in, and the old $20 increased by 0.75%. So this is the new $20. plus our previous $20 that has increased by the 1.0075. And it will have done that one time. After the third deposit, so note that this 20 is the second deposit. This 20 times 1.0075, that was our first deposit. So after our third deposit, our second deposit has seen the growth one time. But our first deposit has seen the growth twice. So once again, this 20 times 1.0075, that's been there for 2 months. So it has grown twice. It was multiplied by 1.0075 2 times. That 20 times 1.0075 to the first, that's because it's had interest one time. And then that blue 20 is the 20 that we just put in. Immediately after our fourth deposit, our first deposit has grown 3 times. Our second deposit has grown twice, and our third deposit has grown once, and our fourth deposit has grown 0 times. You can see that the balance is just ending up being a polynomial. The coefficient is always 20, and the base, what was the x before, is 1.0075. It's a good thing that we can summarize this because after 30 years, that's going to be 360 deposits because we're doing this monthly. I skipped a lot. Notice there are 360 deposits, but the highest exponent is 359 because we started counting at 0. Everybody okay with that? That first term, 20, is 1.0075 to the 0 power. If you start counting at 0, then you'll get to 360 terms when the exponent is 359. Started counting at 0. whole extra term before the first power. Now, this is not something I want to punch into my calculator. There are 360 terms. That sounds awful. But fortunately for our heroes, we just work out with polynomials a summary. First of all, I'm going to factor out the 20, and that's going to leave behind a 1 plus 1.0075 plus 1.0075 squared, all the way up to 1.0075 to the 359. Although I wrote the parentheses in the wrong place. We don't want to punch in 360 terms. So we'll use a little bit of algebra. And we can write this as 1.0075 to the 360 minus 1 over 1.0075 minus 1. Let me just grab our calculating machines. Check our order of operations. This operation is going to do 1.0075 to the 360, then subtract 1 and keep that together. And then 1.0075 minus 1 in parentheses. We'll divide those two and multiply by the 20. So not bad, 36, 614, 87. Moreover, this would be pretty easy to modify for different levels. So 10 years. $10 years would be 120 deposits. So that'll be 3,800. $20 years, we can go 240. $30 years, we'd already done. 36. We could long haul this. So this didn't get us to the 500,000 that we want, but we learned some stuff. We learned that in this calculation, the most important thing that we can bring is time. If you think about retiring at 60, this 10 years would be starting at 50. Way too late. 20 years would be starting at 40. 30 years would be starting at 30. 40 years would be starting at 20. Look at the difference between starting at 20 and starting at 50. Now remember, this is still just 20 bucks a month. $93,000 is not a lot of money, but this is still only 20 bucks a month. This 3870 came from 20 times 120, 2400. This 13357 came from 480 or 4800. This 36614 is from 7200. And the 93626 is from 9600. Any questions? It's really easy to say things like, you should start saving for retirement now. The only reason I mentioned 18 is because at 18, your signature is legally binding, and you can start doing it. The argument is usually made to say, well, I can't afford to do this, even $20 a month. But if you plan on living towards retirement to that age, you kind of can't afford not to. This was 20 bucks a month. At 20, you could reasonably do that for 40 years. Now, this is also just doing 20 bucks a month the whole time. Presumably, hopefully, at some point in the future, by the time you get to age 40, 20 bucks a month will be nothing. And that amount can increase. But notice that the amount that we're putting away is increasing linearly. Every 10 years is just another $2,400 that we're putting in there. But the return that we're getting, because it's been there for so long, is growing exponentially. And exponential functions eventually beat linear functions, always. Any questions? We can go backwards. We can plug in a number here. Notice that the 20 is occupying the same space that the 100 and the 500 occupied in our previous calculation, the simple interest problem. So if I take out the 20, I just put a P0 here, I can decide on a number. I can decide on what number I want to appear here for each of these time frames and figure out what the monthly is going to be. So my previous calculation, if I just get rid of the 20, that'll see what I multiply the 20 by. That's what I multiply the 20 by. So if I take the 500,000 and divide it by this 4,681, if we put $106.81 away every month for the next 40 years and get 9% return annually, that will get us to $500,000. Big change from the previous, where we had to put $37,000 up front. This one is just over 100 bucks a month. For 40 years, but 100 bucks per month. 5 times our monthly has resulted in more than 5 times after 40 years. Sure. So this is the number. Just take 1,000,000 and divide by 213. Unsurprisingly, it's just twice as much. Because now we're seeing doing this for 40 years at 0.75% per month for 40 years. We double this amount, that'll just double our P naught. So it's not surprising that it just doubled. 9% is pretty stable. I don't know what it would do right now. The important thing to realize here is that this is a long game. Right now, there are a lot of, I'm not a financial advisor, so take this as you will. But you need to think of this as a long game. Right now, there are a lot of people are into cryptocurrency and investing in the stock market and being very active. That makes it more of a gambling game. If you want something safe and reliable, you just go for an index fund, an S&P 500. If you just do that, it'll be more reliable than all these games where you're gambling with money that you probably don't really have. That makes sense? A lot of times people confuse gambling and investing. For example, mathematically, buying lottery tickets is a bad idea. If you think of buying lottery tickets as investing, then you're being an idiot. That is a terrible investment. But if you think of buying lottery tickets just in terms of gambling, then it's fun. It's just a fun thing that you're doing. Because once you think of things in terms of gambling, you only have to worry about one question. When you are gambling, the only question you care about is, can I afford to lose this bet? If you can't afford to lose the bet, you can't afford to place the bet. I don't care how reliable you think winning is. If you can't afford to lose the bet, you can't afford to place the bet. If you can't afford $2 on a lottery ticket, then you can't buy that $2 lottery ticket. Does that make sense? That is the only consideration with gambling. Notice I didn't bring up how likely it is you are to win, what the potential payoff is going to be. If you can't afford to make the bet, you can't afford, if you can't afford to lose the bet, you can't afford to make the bet. If you want to win $500,000, all you have to do is go to a casino and take $250,000 and drop it on black. And also have black show up. But if it comes up red, you're at $250,000 against really a terrible return for such a huge investment. That's because it's not an investment, it's gambling. And so when you walk into the casino with your child $250,000 to save for their education, you think, well, I'm having another kid, so I'm going to have to bet this and double up. You can't afford to make that bet because you can't afford to lose that bet. If you're in a position where you can afford to spend $4 a week on the lottery, you might as well. If it's going to be fun, then you might as well, because it's gambling, and gambling should just be a fun thing. Does that make sense? All because of polynomials. Moreover, this is very adjustable. This 0.7, the 1.0075, that's easy to change. What if we expect a 12%? Then it's going to be 1.01. We can see how that would affect things. Let's take that 20 and okay, let's go in like the next. Instead of 1.0075, what if we got 1% per month? That would be a lot. That would be over 12% per year. But there's our multiplier at 1% per month, nominally, over 12% per year. So times 20, $235,295. Any questions? That's just 0.25% increase per month. I bought a car once, and I was buying it. I was going to make payments on the car, and I was pre-approved at a certain percentage rate. And so I sat down with the finance guy, and they were offering. They wrote up the paperwork as if it wasn't pre-approved, going through their financing, and it was a 1/4 point higher. I'm like, oh, dude, I told you I was pre-approved. This is a 1/4 point higher. And the guy had the balls to say, it's only a 1/4 point. To which I responded, well, then fuck you, you pay it. If it's only a 1/4 point, you pay the 1/4 point. And he's like, but I expected that because he's the car salesman finance guy. So. So, it's easy to say you should start saving for retirement now, but at least if you run the numbers, you can see why you can start saving for retirement now. Offer does not apply for 17 years old because you're sorry. Any questions? I know there's not a lot of trig, but it is tangentially related to trig because what we're talking about? Roots of numbers, which is very related to polynomials. And this was just a polynomial problem combined with an exponential function problem, but it was just a polynomial problem. You can make similar kind of calculations to figure out what the monthly payment is going to be on a house. So you can figure out how much house you can afford. Although arguing from monthly payments is a very dangerous thing. If you walk into buy, and it's going to be especially true if you're going to buy a car. If you go in to buy a car and they ask you what the monthly payment is, you do not answer that question. If I find out that a car salesman asks you how much you want to pay per month and you answered them, I'm going to come and drag you out that dealership. That's my superpower. Any of my students walk into a car dealership, I immediately know. And when I can hear the car dealer say, how much do you want to pay per month? And if the student starts to say a number, I can immediately use my action to teleport to that student. And then as a bonus action, remove the student from the car dealership. And the verbal component of this spell is, the hell are you thinking? I told you not to answer that question. They're not your friend. You think they're your friend because they're friendly. They are not your friend. Their superpower is to make sure that you think they're your friend. They're really good at it too. You know what I mean? Hey. What are you talking about? Oh, yeah. Find a way to make a retirement account. Start putting some money away. That's going to do it for today. I will see y'all on Thursday. I know we didn't do a lot of trig today, so get some trig questions and we'll talk about them on Thursday. That's it for today. See y'all on Thursday. Everybody have a good couple days and thanks for playing.